question is draw the TCI compartment model, the multi-compartment model, and then compare and contrast Marsh and Schneider. So again, we've drew it in the other video, so we know how to draw it. Then we talk about what x to kxy, which is a rate constant from the compartments. An x to y constant fraction of the drug that is transferred from x to y per unit time. So that's just saying basically what the xy is, right? So the x to the y is a fraction of the drug, which is a constant, right? So the compartments is theoretical volumes in which the drug distributes. VDSS, which is V central plus V2 plus V3. That's at steady state. Now KEO is equilibration rate constant. Okay, so between plasma and effect site. And then K10 is the elimination rate constant, which talks about clearance. Effect site is negligible volume. And I also did want to mention here briefly that KEO is based on pharmacokinetics and pharmacokinetics and the fixed formula, while loss of consciousness. I'll get back to you. Give me a second. This is what I was trying to get. Time to peak effect is based on KEO and pharmacokinetic principles, but is not dependent on the dose. And time to loss of consciousness is obviously dependent on the dose and the KEO. Yeah, this is pretty much it. KEO, just for understanding, KEO describes the difference between, is basically described by the Fick's law. And then a high KEO, as you can see here, means a smaller half-life, which means a faster time to equilibration and a time to peak effect if we're talking about a bolus. But a low KEO means a larger half-life, a slower time to infusion, and time to peak effect. Now, why is that relevant? Because time to peak effect is based on the KEO. So if you have a higher KEO, then you have a quicker time to peak effect, right? But the time to loss of consciousness is different. Time to loss of consciousness is basically when it reaches that and is dependent on the dose and obviously the KEO, because the higher KEO would mean that the slope will be, quicker. So time to loss of consciousness is obviously based on the dose, but it's also based on the KEO. Time to peak effect is not based on the dose because it's constant for any of the drugs. Whether you give 2 mils or you give 500 mils, you still get the same time to peak effect, which is 1.6 minutes. But it's dependent on the KEO. So a higher KEO, which is basically the lag time, and the PK factors of the patient, obviously. So I've just derailed a bit, but let's go back to Marsh and Schneider. And we explained how you remember that, because we said for Marsh, the only thing that's variable is all the VDs, V1, V2, V3, and it's all based on the height. And for Schneider, which is an effect site, right, the variable ones are the V2, which is based on age, because Schneider has a 2-year-old son, and the K10. But fixed is V1 and V3, and K13, K31, because that's the constants, and then KEO, which is 0.46. And so we know that all the constants are fixed, and the K10, which is the clearance, is fixed in Marsh, and KE0 is 0.2. So based on plasma, healthy patients, small cohort, greater variability with weight and age and lean body mass, obviously should include that. All right, so for bolus dose, for Marsh is harsh, right? So you have increased bolus, which is increased weight. Marsh is harsh. Increased bolus V1, overdose risk, especially in obesity and elderly, no moderate for age, and therefore risk of overdose. Time to peak effect is 4 to 5 minutes, which is 4.5 minutes, which is 4 to 5 T-half KOs, which is about 4.5 minutes. Reduced KO increases half-life and plus increases V1, where time to peak effect is 1.6 minutes. You have a decreased bolus, BMI 45 and 35, paradoxical low BMI at high a paradoxical low lean body mass at high. So when you have a really high BMI, it actually gives you a low lean body mass, which is wrong. So the BMI is 45 and that. So due to the James formula calculation, better for elderly will adjust the bolus and the infusion rate. So basically, what you wanna say is BMI greater than 45 and 35 is not good for female based on the James formula. Anything above that, basically, you have a low lean body mass for some reason. So, and the reason is at higher BMIs you get a low lean body mass. The reason why that happens is because lean body mass in James formula is 1.1 times W minus 128 times W over height squared. Now, if you have someone who's really fat, this number goes up, but this number goes up crazily. So then you get like a negative number. So the lean body mass is really low. Obviously, when someone is fat, they have increased total body weight and also increased lean body mass. So that way, that doesn't work. So we need this equation for a different question, but it's important to know lean body weight is 1.1 times total body weight minus 128 total body weight over height squared, and for females it's 148. So I will figure out a way how to remember it, but that's just it.